Today I want to talk about how to calculate the magnitude and direction of a magnetic force acting on a charge moving through a magnetic field, and to do a few examples with that. So, imagine we've got some charge Q, which could be positive or negative, moving with a velocity vector V through a magnetic field B. Well, this cross product gives the expression for the magnetic force acting on that charge. So, you can think of it two different ways. One, you've got the charge, which could be positive or negative, multiplied by the cross product of the velocity and the magnetic field. Or you could think of this as a cross product of two vectors. A vector, Q times V, that would be the first vector in the cross product, and B would be the second vector in the cross product. For our purposes, that might be the easiest way to think about it. Okay, so from what we know about cross products, we can get the magnitude and direction. The magnitude, well, the magnitude of any cross product of two vectors, you take the magnitude of the first vector, so there's our first vector, that magnitude of charge Q times velocity vector V would be absolute value Q times magnitude V. Magnitude of the second vector, B, is just magnitude B. And then you need to take the sine of the angle between the first vector and the second vector in the cross product. So all that appears here. This is just from the definition of a cross product. There's two parts. We've got a magnitude and a direction. The direction is given by the right-hand rule. Now the first thing we need to know is if you're taking a cross product of two vectors, the result will be perpendicular to both of those vectors. The right-hand rule is just a way of telling which of those two directions to take. So here's the rule. Put your finger of your right hand, your first finger of your right hand, in the direction of the first vector in the cross product. Put the second finger of your right hand in the direction of the second finger in the cross product. Your thumb will point in the direction of the cross product, which in this case is the force acting on the charge. The other way to do it is to put your fingers in the direction of the first vector, fingers of your right hand in the direction of the first vector, curl them into the direction of the second vector, your thumb will point into the direction of the cross product. So I've got three examples. I'm going to find the direction of the magnetic force on the moving charge using both of those right-hand rule schemes, which give you the same result. Okay, so here I have a positive charge moving this way, and a magnetic field is pointing this way. So to find the direction of the magnetic force on this charge, I'll stick my finger in the direction of Q times V. V is this way, the charge is positive, so Q times V is in the direction of the velocity. The magnetic field is directed this way, so the magnetic force will be in the direction of my thumb, or out of the board. All right, I could do it the other way. Put my fingers in the direction of Q times V, again using my right hand, because if you use your left hand you get everything backwards. Curl them into the direction of the magnetic field, and then my thumb points in the direction of the magnetic force acting on the charge. Again, out of the board. Great. So no matter how you slice it, the magnetic force on this positive charge moving this way in the magnetic field that way is out of the board. Let's try this one. Now, here I've got a negative charge. So the velocity is this way, but Q, charge times velocity, is this way. If you have a negative number multiplied by a vector, the direction of the resulting vector is just opposite the direction of the original one. So if V is this way and Q is negative, then Q times V is that way. So I'll stick my first finger of my right hand in the direction of Q times V. My second finger goes in the direction of the magnetic field. Boom. Now where does my thumb point? My thumb points out. So again, I've got a force that's out of the board. Or using the hand method, if you will, Q times V is this way, so I stick my fingers in that direction, curl them in the direction of the magnetic field, and my thumb points out. So again, force is out. One last example. Now these X's are going to represent a magnetic field into the board. So imagine that each of these X's is really a line. Whoosh, magnetic field this way, magnetic field that way, magnetic field that way. Magnetic field is pointing into the board. And this is just a way of representing that. If you want to represent a magnetic field pointing out of the board, you'd have little dots. Okay, So now, V is this way, the direction of the velocity, but I've got a negative charge moving in the magnetic field, so Q times V is that way. So I stick, using my right hand, stick my first finger in the direction of the velocity. Now my second finger's got to somehow go in the direction of the magnetic field, so I got to get it around there. So this direction of the velocity, direction of the magnetic field, and my thumb then will point in the direction of the force. All right, so it looks like the force is that way. Now I've got to draw that so it's perpendicular to the velocity. Draw it that way. There's the direction of my force. So that's got to be perpendicular, and it's also perpendicular to the magnetic field. And whenever you do these things, you should check to make sure that when you're done, the force you've drawn or indicated or said or whatever is perpendicular to both that and that. If it's not, then you haven't done it correctly. All right, so I still need to do it with the other method. So using the hand method, the velocity is this way, but I got a negative charge, so Q, the charge times the velocity, is this way. So stick my fingers in the direction of Q times V. Now I've got to curl them into the direction of the magnetic field, which is into the board. So I've got to actually do this. So fingers in the direction of the velocity, curl them into the direction of the magnetic field, and my thumb will point in the direction of the force that way, just as we calculated before. Great. So that's how you deal with directions. You can expect to see one of these, something like this, on an exam, possibly as a multiple choice question or short answer. All right. Now, to calculate the magnitude, it's just a matter of plugging and chugging. If you know the charge, you know the velocity, if you know the magnetic field, and you know the angle between the the velocity, or rather the charge times the velocity in the magnetic field, which you can plug in there, then you can just crunch out the force. But I want to give you a trick question. So look here, let's see if we can figure out the expression for the magnetic force on this charge. Now let's just say this charge has value Q. Let's say we know V, we'll just call it the magnitude of that V without the arrow. We know the value of the magnetic field. We're not going to plug in numbers, but I want to know which of these two expressions, this one or this one, would be correct for finding the magnitude of the force on this charge, the magnetic force due to the magnetic field. Well, you're going to be tempted to use this 20-degree angle that I've put in the picture because I've put it in there. And that 20-degree angle is a perfectly respectable angle. It gives us the direction of the velocity relative to the rightward direction on the board. It'd say, well, the velocity vector is directed at 20 degrees below the rightward direction. Great. But the theta that I want in this expression is the angle between Q times V and the magnetic field. Well, let's think about whether the 20-degree angle is correct for that. Q times V is this way. The magnetic field is this way. So those are right angles to each other. So the theta that I want for this expression is actually 90 degrees. The sine of 90 degrees is 1. So I actually have QV times B times sine of 90 degrees, but sine of 90 degrees is 1. So really this is the right expression. This is Q times V times B times sine of 90 degrees. So I've got a 1 in here. So this is the right one. This is just a distractor using an angle that's not relevant. So be careful about that in case someone tries to trip you up. Okay, that's all. Thanks for watching.